There is a problem with time that becomes harder to ignore the more accurately we learn how to measure it. For most of human history, nobody had to think too deeply about what time actually was. You watched the sun move across the sky, you measured the seasons, you built mechanical clocks, and eventually you built increasingly precise atomic clocks. The assumption was always that the clock was measuring something that already existed independently. Time was there, and the clock simply told you how much of it had passed. But modern physics has gradually made that picture much harder to defend. We now know that two clocks can start together, follow different paths, and return with different amounts of elapsed time recorded on them. We know that the rate at which a clock runs depends on its motion and its position in a gravitational field. We have measured differences in the passage of time across distances of about a millimeter. We have built quantum systems where the order of events can become indefinite. We have theoretical descriptions of the universe in which the ordinary variable representing time disappears altogether. And now researchers are developing clocks so precise that they can test whether the fundamental constants controlling the behavior of matter have remained constant throughout history. None of this means that time is an illusion in the simple sense. You still age, objects still move, and events still happen in an order that matters to everyday life. The problem is that physics is increasingly suggesting that the time we experience may not be a basic ingredient of reality in the way we normally assume. It may instead emerge from relationships between physical systems, from information, from entropy, or from something deeper that we have not figured out yet. The uncomfortable part is that we do not currently know which explanation is correct, and the experiments that are supposed to help us answer the question keep making the situation more complicated. One of the clearest examples comes from an atomic clock built around a single aluminum ion. The experiment is not using a large mechanical mechanism with gears or a pendulum swinging back and forth. The clock is based on the behavior of one atom that has been stripped of an electron and held in place using electromagnetic fields. The system is cooled to extremely low temperatures so that unwanted motion does not interfere with the transition being measured. The result is a clock capable of reaching the 19th decimal place of precision, improving on the previous record at the 18th decimal place. At first, that might sound like an achievement that only matters to people who build clocks, but the reason this precision matters is much bigger. An atomic clock does not just provide a more accurate way of telling the time. It gives researchers an extremely sensitive way to look for changes in the physical laws that determine how the atom behaves. Some of the most important numbers in physics are treated as constants. The fine structure constant, for example, describes the strength of the interaction between electrons and light, while the gravitational constant determines the strength of gravity. We normally put these values into our equations as fixed quantities. But physics does not simply assume that every constant must remain unchanged forever. If something were changing extremely slowly, the only way we could know would be to measure it at different times with enough precision to detect the difference. That is where clocks become more than clocks. If a clock is accurate enough, a tiny change in an underlying constant could alter the frequency of the transition used to define its ticking. Researchers could then compare that behavior over time and ask whether the laws governing the clock itself are drifting. That creates a strange conceptual problem. If one of the fundamental constants were found to be changing, then the laws of physics would have a history. There would be a value at one point in time and another value at a later point in time. But to describe that change, you already need the concept of time. You cannot simply say that a constant changed without some notion of before and after. That means time would have to be part of the framework in which the laws evolve. If the laws of physics are supposed to explain where time comes from, then you have a problem because you are using time to describe the changing laws before you have explained what time itself is. This is one reason the definition of the second is so revealing. Since 1967, the second has been defined using the frequency of a transition in cesium. The number is 9,192,631,770 cycles. That gives scientists a tremendously precise standard, but notice what the definition actually does. It does not explain what time is. It tells us how to establish a reproducible unit of time using a physical process. That distinction becomes important when we ask deeper questions. Physics is extremely good at describing what happens to clocks. It can calculate how a clock changes when it moves quickly, how it changes when it's placed at a different gravitational potential, and how different clocks should compare after taking different paths through spacetime. But describing the behavior of clocks is not exactly the same thing as explaining what the underlying quantity being measured actually is. This is where the story moves from engineering into fundamental physics, because the idea of time as a universal background was already challenged more than a century ago. Newtonian physics treated time as absolute. It was assumed to flow independently of everything else. A second was a second everywhere, and the universe simply existed inside that universal flow. Einstein's relativity changed that picture. Time became connected to motion and gravity, and the amount of elapsed time recorded by a clock could depend on the path that clock took through spacetime. This is not just a theoretical possibility. In 1959, Robert Pound and Glenn Rebka tested gravitational redshift using gamma rays traveling up a 22.5-meter tower at Harvard. General relativity predicted that the gravitational field would cause a tiny frequency shift. They measured it, and the result agreed with Einstein's prediction. The implication is that clocks at different gravitational potentials do not run at exactly the same rate. The clock lower down runs slightly slower than the clock higher up. The difference is tiny under ordinary conditions, but it is a real physical difference. Then in 1971, Joseph Hafeil and Richard Keating carried cesium atomic clocks on commercial flights around the Earth, while other clocks remained on the ground. When the clocks were compared, they did not agree perfectly. Again, the clocks were not malfunctioning. They had simply followed different paths through spacetime with different velocities and different gravitational environments. The amount of proper time accumulated along those paths was different. This is one of the most important ideas in relativity because it removes the need for a single universal clock somewhere in the background. Two clocks can legitimately disagree about how much time has passed between two events because the amount of elapsed time depends on their physical trajectories. You might think this is something that only matters when you are flying around the planet at high speed, but it has become part of ordinary technology. GPS satellites orbit roughly 20,000 kilometers above Earth and carry atomic clocks. Their motion causes their clocks to run at a different rate from clocks on the ground, while their position in Earth's gravitational field produces another effect in the opposite direction. When the effects are combined, the satellite clocks run faster relative to clocks on Earth's surface by roughly 38 microseconds per day. 38 microseconds sounds insignificant, but GPS is based on timing. A receiver determines its location by comparing the arrival times of signals from multiple satellites, and light travels about 30 centimeters in a nanosecond. Tiny errors in timing therefore become errors in distance. If the relativistic corrections were ignored, the resulting positioning error would grow to roughly 11 kilometers per day. So, the strange fact that time does not pass at exactly the same rate everywhere is not just something physicists write on a blackboard. Your navigation system depends on it. The phone in your hand is using technology that works because engineers account for the fact that clocks in different places and under different conditions do not necessarily agree. The remarkable thing is how small the differences can now be while still being measured. In 2021, researchers in Boulder measured gravitational time dilation across a vertical separation of about 1 millimeter. That is an incredibly small distance compared with the scale on which gravitational effects are normally discussed. You do not need to compare a clock at sea level with a clock on a mountain anymore. With sufficiently precise instruments, the difference in gravitational potential across a tiny vertical separation becomes detectable. The precision reached approximately 7.6 times 10 to the minus 21. At this point, the effect becomes personal in a strange but perfectly literal sense. Your head is slightly farther from the center of Earth than your feet are, so the gravitational potential at your head differs slightly from the potential at your feet. That means the rate at which time passes at the top of your body differs slightly from the rate at the bottom. The effect is far too small to feel and has no practical impact on your daily life, but it is physically there. There is no single perfectly uniform rate of time passing through your entire body. The difference is incredibly small, but modern clocks are now sensitive enough to detect effects on that scale. This also changes how we think about the idea of a universal present. If two clocks at different heights accumulate different amounts of time, and clocks moving relative to one another can also accumulate different amounts of time, then there is no simple universal clock that everything in the universe is following. Relativity goes even further because simultaneity itself is not absolute. Two events that are simultaneous according to one observer may not be simultaneous according to another observer moving relative to the first. This is not simply a matter of light taking time to reach different observers. The disagreement is built into the structure of spacetime. There is no single cosmic slice of reality that every observer can point to and call now. Your present is defined relative to your physical situation. Another observer moving relative to you can divide events into past, present, and future differently, while both descriptions remain consistent with relativity. The twin example makes this easier to understand because it turns an abstract statement about spacetime into something human. Scott Kelly spent close to a year aboard the International Space Station while his identical twin brother Mark remained on Earth. When Scott returned, the difference between their accumulated elapsed times was around 5 milliseconds over roughly 340 days. 5 milliseconds is far too small to see, and it does not mean one brother suddenly looked younger than the other. But the physical difference was real. They had followed different paths through spacetime, and their clocks did not record exactly the same amount of elapsed time. That is a very different idea from the old picture in which there is one universal time flowing through the entire universe and every clock is simply trying to keep up with it. In relativity, the clock is not merely displaying a universal quantity. Its reading depends on its path. But relativity creates another question that is even harder to answer. We understand why clocks can run at different rates, but why does time seem to have a direction? Your memories point toward the past. You do not remember tomorrow. A glass can fall and break, but you never watch the broken pieces spontaneously assemble themselves into the original glass. Coffee cools after being poured, but you do not normally see the room spontaneously transfer heat into the coffee until it becomes hotter than it was before. The world around us has an obvious distinction between past and future, yet many of the fundamental equations used in physics do not contain an equally obvious built-in direction. If you reverse the direction of time in many of the equations, they continue to work. That creates one of the oldest and most important problems in physics. Why does our experience have a direction if the microscopic laws do not seem to require one? The standard explanation involves entropy. Ludwig Boltzmann's work helped establish the statistical picture in which entropy tends to increase because there are vastly more disordered configurations than highly ordered ones. A perfectly arranged deck of cards represents a very special state. There are enormously more possible shuffled arrangements than there are perfectly ordered arrangements. Nothing in the microscopic laws necessarily makes the ordered arrangement impossible to recreate, but the probability of a random process producing that exact special state is extremely small. In this picture, the direction of time that we experience is connected to the statistical behavior of large numbers of particles. The universe appears to have begun in a remarkably low entropy state, and from that condition, entropy increased. That gives us the thermodynamic arrow of time. But it also creates another problem because now we have to explain why the universe started in such a special low entropy condition in the first place. The statistical explanation tells us how an arrow can emerge once you have the right initial condition, but it does not automatically explain why the initial condition existed. This becomes even more interesting when physicists look at quantum systems. Researchers studying open quantum systems at the University of Surrey examined how an arrow of time might emerge when a quantum system interacts with its environment. One expectation is that the environment should provide a source of irreversibility because information about the system becomes distributed into the surroundings. Once that information has spread into an enormous number of degrees of freedom, reversing the process becomes practically impossible. But the analysis described in the source found that, even after accounting for the environmental interaction in the usual framework, the memory kernel remained symmetric with respect to time. In other words, the mathematical description did not simply hand us a one-way arrow. The expected asymmetry was not sitting there as an obvious microscopic ingredient. That raises the possibility that the arrow we experience may be connected to information. This is where the work of Rolf Landauer becomes important. In 1961, Landauer showed that information has a physical cost. If you have a physical system that can represent a bit as one of two states, and you erase that information by forcing the system into one definite state, the process has a thermodynamic cost. At a given temperature, there is a minimum amount of heat that must be dissipated when one bit is erased. At room temperature, that lower bound is around 3 times 10 to the minus 21 joules per bit. The amount is extremely small, but the principle is significant because it establishes that information is not completely separate from physics. A memory is a physical state. Erasing that memory is a physical process. The transformation has thermodynamic consequences. This prediction was later tested using a microscopic particle in a double well system. In 2012, researchers measured the energy dissipated when one bit of information was erased and found that the result could approach the thermodynamic bound predicted by Landauer's principle. This matters for the question of time because the world is full of physical records. A memory is a record. A photograph is a record. A measurement stored in an instrument is a record. A scratch left on a surface is a record. These are all physical changes that correlate a present state with something that happened previously. The fact that records exist is closely connected to the fact that we experience a distinction between past and future. We remember the past because physical information about previous states has survived into the present. We do not remember the future because there are no corresponding physical records of events that have not occurred. That does not mean consciousness creates time, and it does not mean that a human observer is required for reality to exist. The important point is more basic. A physical system must interact with something if information about an event is going to become encoded somewhere. The recording process itself is physical, and physical recording has thermodynamic consequences. That makes the connection between information, entropy, and temporal direction much harder to dismiss. The quantum version of this idea gets even stranger. Researchers at Oxford built an extremely small clock using a double quantum dot, where a single electron can move between two tiny regions on a chip. Each jump can serve as a tick. In ordinary life, we do not think about the energy required to read a clock. You look at the display and learn the time, and the process seems practically free. But when the clock is reduced to a quantum system, the act of extracting information from it becomes physically important. The reported result was that reading the clock could require up to 1 billion times more energy than the physical process responsible for producing the ticks. The clock itself could operate comparatively cheaply, while obtaining information about what it had done could be much more thermodynamically expensive. That is a very important distinction. There's a difference between a system changing and another system acquiring a record of that change. If an electron moves between two quantum dots, the physical transition happens whether or not a person knows about it. But to use that transition as a clock, information about the transition has to become available. The act of measurement produces entropy, and the source describes an important result from the experiment. When the two quantum dots were at the same temperature, the electron could jump in either direction with equal probability, and there was no preferred thermodynamic direction. The arrow emerged in connection with the measurement process. Again, this does not show that somebody looking at a clock magically creates the future. It shows that measurement, information, and thermodynamic irreversibility are physically connected. This gives us a very different way of thinking about the passage of time. Perhaps what makes the past different from the future is not that there is a fundamental cosmic substance called time flowing in one direction. Perhaps the difference emerges because the physical universe accumulates records. A state at one moment contains information about earlier states, while the future has not yet left those records. But this immediately creates another problem. If the arrow of time depends on records, what happened before there were records? And if records require physical systems, where did the first temporal direction come from? You can see how quickly the explanation becomes circular. Quantum mechanics makes the problem more serious because time has a peculiar status inside the theory. Position is treated as an observable. Time normally is not. In ordinary quantum mechanics, time is an external parameter that tells the quantum state how to evolve. The theory is extraordinarily successful, but it quietly assumes the existence of the thing we are now asking it to explain. You can use quantum mechanics to describe what happens to a system as time passes, but if you want a theory that explains the entire universe, you cannot simply place the universe inside an external clock and then ask what the clock outside the universe is doing. There is no outside. This is where experiments involving quantum causal order become relevant. In classical physics, if you have two operations, there is a definite order. Either our operation A happens first and operation B happens second, or B happens first and A happens second. You might not know which order occurred, but the order itself is assumed to exist. Quantum mechanics allows a more unusual possibility. Work involving Giulia Rubino and collaborators in Vienna explored situations in which two operations can exist in a quantum superposition of different orders. The system can be described as though A happened before B and B happened before A. This is not simply uncertainty caused by incomplete knowledge. The causal order itself can become indefinite within the quantum description. That does not mean that everyday events have no order. Your alarm goes off before you get out of bed. You drop a glass before it hits the floor. Classical causality remains extremely useful and accurate at ordinary scales. But the deeper quantum description does not necessarily have to begin with the same fixed temporal structure that our everyday experience suggests. If causal order can be a quantum property rather than a permanent background, then the assumption that before and after are fundamental may need to be reconsidered. The problem becomes even more serious when physicists try to describe the entire universe quantum mechanically. General relativity describes space-time as something dynamic. Quantum mechanics describes quantum states evolving. Both theories have different ways of dealing with time, and combining them is one of the central problems of theoretical physics. The Wheeler-DeWitt equation, developed by John Wheeler and Bryce DeWitt in the late 1960s, is one of the most famous examples of what happens when you try to quantize the universe as a whole. The ordinary time variable that appears in standard quantum evolution disappears from the equation. The universe is described without an external time parameter in the usual sense. That produces what is often called the problem of time. If the fundamental equation describing the universe does not contain the ordinary variable representing time, then where does the time we experience come from? You cannot put a clock outside the universe because the clock would itself be part of the universe. There is no external observer standing beyond reality and watching the cosmos evolve. This leads to the possibility that time might be relational rather than fundamental. Don Page and William Wooters developed an approach based on this idea. Instead of imagining the universe as a system evolving against an external clock, you can consider correlations between different parts of the universe. One subsystem can effectively act as a clock relative to another subsystem. An experimental demonstration involving entangled photons explored this kind of idea. One photon could serve as a clock, while another functioned as an internal system. From an external description, the combined state could appear static. But from the perspective of the internal subsystem, correlations with the clock photon could produce what looks like ordinary evolution. In other words, you can get a meaningful experience of time from relationships inside a system, even if the entire system does not require an external clock. This is a very different idea from saying time is imaginary. If you are part of the universe, your physical state changes relative to other physical systems. Your brain contains records of previous states. Your body undergoes thermodynamic processes. You interact with clocks, light, matter, and gravity. All of those relationships provide a meaningful local structure of before and after. The claim would be that this local structure does not necessarily require a universal time variable existing outside everything else. Black holes make the issue even harder because they bring time and information into the same problem. Stephen Hawking showed that black holes can emit radiation and therefore lose mass over time. The radiation is thermal, which creates a serious question about information. Quantum mechanics requires unitary evolution, meaning that information should not simply vanish. But if a black hole evaporates through thermal Hawking radiation, where is the detailed information about everything that fell into it? If the information is truly destroyed, then the present state of the universe would not contain a complete record of the past. That would be an enormous problem for quantum mechanics and for our understanding of physical history. The black hole information problem remains unresolved, and different approaches attempt to explain how information might survive. But the connection to time is important because our idea of a past depends heavily on the present containing physical consequences of previous events. If information about an event can be permanently destroyed, then the relationship between past and present is not as straightforward as everyday experience suggests. Another experiment takes the idea of time reversal in a completely different direction. Researchers at the City University of New York created a temporal boundary for an electromagnetic wave. Normally, when a wave encounters a boundary in space, it can reflect. A light wave hits a surface and changes direction. In the experiment, researchers rapidly and uniformly changed the physical properties of the medium through which the wave was traveling, creating a discontinuity in time rather than a conventional spatial boundary. The result produced a time-reversed component of the wave. This does not mean that a person can enter the experiment and travel into yesterday, and it does not create a time machine. The physical world outside the engineered system continues normally. What the experiment shows is that wave behavior can exhibit a form of temporal reflection when the physical conditions of the system are changed in the appropriate way. It is another example of how the equations governing microscopic and electromagnetic processes can permit behavior that does not fit neatly into our everyday intuition about the direction of time. At this point, it might seem as though fundamental physics is telling us that time reversal is always possible, and the arrow of time is entirely an illusion. But that would also be too simple. Particle physics contains genuine examples of time reversal asymmetry. The Babar experiment reported direct evidence of time reversal violation in certain subatomic processes, and the T2K experiment in Japan found related asymmetries involving neutrino oscillations. These are not the same thing as the thermodynamic arrow of time. They represent a different type of asymmetry in fundamental particle behavior. The important point is that physics contains multiple different meanings of time direction. Thermodynamics has one arrow. Particle physics has another kind of asymmetry. Quantum theory allows indefinite causal order in certain situations. Relativity removes the idea of universal simultaneity. These facts do not necessarily contradict one another, but they also do not yet fit together into one simple explanation of what time fundamentally is. Then there is the quantum Zeno effect. A quantum system can evolve from one state to another, but if you measure it repeatedly at sufficiently short intervals, the evolution can be slowed down. In the ideal limit of continuous observation, the transition can effectively be suppressed. The system appears to remain in its original state because it is being checked so frequently. This does not mean that human attention is controlling reality. The measurement can be performed by a physical apparatus, but it does show that the act of measurement can affect the evolution of a quantum system. That becomes particularly interesting when combined with the other experiments involving clocks, information, and entropy. The physical process that extracts information about a system can influence the system, and the act of recording information has a thermodynamic cost. So measurement is not a passive window through which we simply look at a pre-existing process. At the quantum level, the measurement interaction can be part of the physical process itself. There is another experiment that pushes this idea further by measuring a quantum transition without relying on an external clock in the usual way. The work involving Hugo Dill's team at EPFL in February 2026 looked at an electron absorbing a photon and moving into a higher energy state. Normally, if you want to measure how long a process takes, you compare it against something external. You start a clock, observe the event, stop the clock, and calculate the difference. But that procedure assumes that an external duration already exists. The researchers instead used information generated inside the quantum process. The electron can follow multiple quantum pathways, and those pathways interfere. The resulting interference leaves information in the spin of the emitted electron. By analyzing that information, researchers could infer the duration of the transition from the system itself. That transition was not instantaneous, and the measured duration depended on the structure of the material. Changing the symmetry of the crystal altered the transition time, with lower symmetry producing a longer transition and higher symmetry producing a shorter one. The significance is not that scientists have proven time is literally created by crystal geometry. They have not. The important result is that duration can be extracted from the internal physical structure of a quantum event rather than simply being imposed from an external clock. That adds another example to a growing collection of experiments in which time appears increasingly connected to relationships, interactions, and physical processes, rather than behaving like an independent background substance. And then, the problem appears at the largest possible scale. Cosmologists have a disagreement over the expansion rate of the universe known as the Hubble tension. One method, using observations of the cosmic microwave background, together with the standard cosmological model, gives a value around 67.4 kilometers per second per megaparsec. Another method, based on Cepheid variable stars and the cosmic distance ladder, gives around 73.2. The difference is approximately 5 sigma. The significance of this disagreement is not simply that two groups measured different numbers. The Hubble constant is connected to the history of cosmic expansion, and our reconstruction of the universe's past depends on how that expansion evolved. If the underlying cosmological model is missing something, then our description of cosmic history may need to change. Observations from the Dark Energy Spectroscopic Instrument in 2024 added another potential complication. The data suggested that dark energy may not behave exactly like a constant and may have been stronger earlier in cosmic history while weakening over time. If that result survives further testing, it would mean that one of the major ingredients in the standard picture of cosmic expansion changes with the evolution of the universe. Again, this does not mean that somebody's watch is literally running differently because dark energy is changing. The issue is deeper. Our reconstruction of the universe's history depends on the physical model used to describe its expansion. If that model changes, the way we reconstruct cosmic time changes with it. That is why some of the most important experiments happening now are focused on clocks. The ACES experiment aboard the International Space Station carries highly precise clocks, including a cold atom cesium clock and a space hydrogen maser, and compares their timing with atomic clocks on Earth. The purpose is not simply to confirm that relativity works. Relativity has already passed an enormous number of tests. The interesting possibility is finding a deviation, a tiny discrepancy, that would indicate that our current description is incomplete. If general relativity and quantum mechanics are both extremely successful, but describe time in fundamentally different ways, then the place to look for new physics is where their predictions become distinguishable with sufficient precision. There is another class of clocks being developed around thorium-229. Traditional atomic clocks use transitions involving electrons, but a nuclear clock uses a transition within the nucleus. Because the nucleus is shielded by the surrounding electrons, a nuclear transition can be less exposed to some environmental effects that disturb ordinary atomic transitions. That makes nuclear clocks potentially useful for testing whether fundamental constants remain constant. If a quantity associated with the strong nuclear force were slowly changing over time, sufficiently precise measurements could potentially reveal it. Once again, the clock becomes more than a timekeeping device. It becomes a probe of whether the laws of physics themselves have remained unchanged. The same logic leads to one of the more unusual proposals described in the source. In July 2025, Igor Pekovsky, Jacob Covey, and Johannes Beauregard described a protocol involving an atomic clock placed in a quantum superposition of two different heights. We already know that gravitational time dilation depends on height. A clock higher above Earth accumulates time at a slightly different rate from a clock lower down. Normally, you would have one clock at one height and another clock at another height and compare them. But quantum mechanics allows a physical system to occupy a superposition of different states. If the clock is placed in a superposition of different heights, then the two gravitationally different rates can become part of the same quantum state. The proposal is designed to explore the intersection between quantum mechanics and gravitational time dilation. If such a system can be realized and controlled, it would allow researchers to ask what happens when the relativistic structure of time itself becomes part of a quantum superposition. That is an important step because the central conflict between general relativity and quantum mechanics has always involved more than just gravity. General relativity says that space-time is dynamic and that gravity affects the geometry through which time is measured. Quantum mechanics normally assumes a background time parameter against which quantum systems evolve. If you try to quantize gravity, you eventually have to confront the possibility that the clock itself becomes quantum. The experiment then stops being about measuring a quantum object with an ordinary clock and starts becoming a question about what happens when the thing doing the timekeeping is itself subject to quantum uncertainty. And that may be where the entire problem is heading. The next generation of clocks is becoming precise enough to measure gravitational differences across microscopic distances. Nuclear clocks could provide new sensitivity to fundamental constants. Space-based clocks can compare different gravitational environments with extraordinary accuracy. Quantum systems can carry multiple possible causal orders. Quantum clocks can potentially exist in superpositions of different gravitational rates. At some point, the old picture of a clock sitting inside an already existing flow of time becomes difficult to maintain. The clock is no longer just measuring time. The physical state of the clock is part of the question. This is also why it is important not to overstate what these experiments have proven. None of them has shown that time does not exist. None has demonstrated that consciousness creates the passage of time. None has proven that the universe is a simulation. None has established that we can travel backward through time. And none has produced a final theory explaining where time comes from. The evidence is much more interesting than those claims because it is more specific. We know that elapsed time depends on motion and gravity. We know that there is no universal simultaneity in relativity. We know that the thermodynamic arrow is connected to entropy and a special low entropy initial condition. We know that information has physical and thermodynamic consequences. We know that quantum measurement can affect quantum evolution. We know that causal order can become indefinite in quantum systems. We know that a theory describing the quantum state of the entire universe can be formulated without the usual external time parameter. We know that different cosmological measurements do not currently fit together perfectly. And we know that increasingly precise clocks are allowing researchers to test these ideas at scales that were impossible only a few decades ago. The disturbing part is not that physics has discovered that time is broken. It has not. The disturbing part is that the closer we look, the less obvious it becomes that the time we experience is a single fundamental thing. The word time may be covering several different physical phenomena. There is the proper time measured along a path through space-time. There is the thermodynamic arrow associated with entropy. There is the asymmetry seen in certain particle processes. There is the parameter used in ordinary quantum mechanics. There is the relational time that can emerge from correlations between subsystems. There is the temporal ordering of events, which quantum mechanics can make indefinite in certain circumstances. These are all connected by the fact that we use the same word for them, but physics has not shown that they all come from one underlying mechanism. This might explain why every time we build a better clock, we seem to create a new problem. A crude clock makes time look obvious because it cannot detect the subtleties. A more accurate clock reveals gravitational time dilation. A still better clock reveals differences across tiny distances. A quantum clock forces us to separate the physical process of ticking from the process of reading the tick. A clock used to compare fundamental constants turns timekeeping into a test of whether the laws themselves are stable. A clock in a quantum gravitational superposition forces us to ask what it means for the clock's own rate to be uncertain. The better the measurement becomes, the less reasonable it becomes to think that time is simply a universal background flowing at one rate everywhere. And there is a final issue that is easy to miss. We often talk about the passage of time as if time itself is doing something. We say time moves forward, we say time passes, we say time flows. But physics does not necessarily require those statements to be literally true. A clock changes state. A physical system evolves, entropy increases, information gets recorded, matter moves through space-time. Quantum states become correlated. We then organize those changes using the concept of time. That is extremely useful, but usefulness does not automatically make the concept fundamental. Temperature is a good example of a quantity that emerges from the collective behavior of particles. You can measure temperature precisely, predict it, right, and build technology around it without temperature being a separate microscopic substance. It is a property of a physical system. The question being asked about time is whether something similar could be happening here. Maybe time is fundamental, and we simply do not yet know how to formulate the final theory correctly. Maybe time is relational and only exists in the sense that physical systems provide clocks for one another. Maybe the arrow of time is largely statistical and comes from the universe's unusual initial condition. Maybe information and records play a deeper role in explaining why the past feels different from the future. Maybe several of these ideas are simultaneously correct at different levels. Or maybe the eventual theory will replace the entire question with a concept we do not currently have. What we can say is that time is not as simple as the clock on the wall makes it look. The clock does not prove that a universal time is flowing through the room. It tells you that a particular physical process has undergone a certain number of transitions. Put that clock on a plane and its accumulated time changes relative to a clock on the ground. Move it higher and the rate changes again. Put two clocks a millimeter apart and a sufficiently precise experiment can detect a difference. Turn the clock into a quantum system and the act of reading it becomes physically significant. Put the clock into a quantum superposition of different gravitational environments, and even its own rate can become part of a quantum state. At that point, the question is no longer simply, what time is it? The more fundamental question is, what physical relationship are we actually measuring when we say that time has passed? And that may be why the results are disturbing. Not because the experiments have shown that the universe is malfunctioning, but because they are gradually removing the assumptions that made time seem obvious in the first place. There is no universal present in relativity. There is no simple microscopic arrow in many fundamental equations. The thermodynamic arrow depends on entropy and an unusually ordered beginning. Information has a physical cost. Measurement can influence quantum evolution. Causal order can become indefinite. The quantum description of the entire universe can lose the ordinary external time parameter. Cosmological observations still contain unresolved disagreements about the history of expansion. And the clocks being built today are becoming sensitive enough to test whether the laws themselves have remained constant. So when you look at a clock and watch the numbers change, you are seeing something real. But you may not be seeing time itself in the way you imagine. You are seeing a physical system change in relation to another physical system, and you are using that change to define duration. That distinction sounds small, but it could be one of the biggest unresolved questions in physics. We know how to measure time. We know how time behaves under gravity and motion. We know how to compare clocks with extraordinary precision. What we still do not know is whether the universe fundamentally contains time at all, or whether time is something that emerges from the way the universe's physical parts relate to one another. And if the second possibility is correct, then the strange thing about time is not that it can slow down, speed up, or disappear from an equation. The strange thing is that the universe may not need a universal clock in the first place. The clocks we build may be telling us something about the relationships between physical systems, while the deeper reality underneath those relationships remains something we have not yet learned how to describe. That is the part physics has not solved. We can measure the ticks, we can compare the clocks, we can test relativity, thermodynamics, quantum mechanics, and cosmology against increasingly precise observations. But after all of that, one question remains. When the universe changes from one state to another, what exactly is the thing we are calling time? Right now, physics can describe the measurement with astonishing accuracy. It still cannot give us a final answer about what the measurement fundamentally means. But there is another way to approach the problem, and it starts with something that seems almost too ordinary to matter. Clocks do not actually measure time in isolation. Every clock measures a physical process. A pendulum swings, a quartz crystal oscillates, an atom changes between energy states, a nucleus undergoes a transition, an electron moves between quantum states. The clock then uses that physical behavior as a reference and assigns a number to it. This sounds like a technical distinction, but it becomes crucial when you start asking whether time itself exists independently of physical change. If absolutely nothing in the universe changed, there would be no physical process that could function as a clock. There would be no event to count, no transition to compare, no record to store. You could still write down the symbol time in an equation, but there would be nothing physical corresponding to the passage from one state to another. This is one reason relational approaches to time are so interesting. Instead of imagining time as an invisible substance flowing through the universe, they ask whether what we call time is actually a way of describing relationships between changing physical systems. That idea goes back much further than modern quantum experiments. In classical mechanics, Newton treated time as absolute, independent of everything else. But Leibniz had a very different intuition. He argued that time should be understood relationally, as an ordering of events rather than as a substance existing independently of them. The modern physics of relativity did not simply prove Leibniz right in every detail, but it did destroy the Newtonian picture of a universal clock. There is no single clock hidden somewhere outside the universe whose reading determines what time it is everywhere. Every physical clock follows its own path through space-time. What makes this especially strange is that we normally build our lives around the assumption that there is a shared present. We schedule meetings at the same time, synchronize computers, broadcast signals, and coordinate experiments. All of this works because at ordinary scales, the relativistic differences are tiny enough to ignore. But when you push the measurements far enough, the shared present stops being a fundamental concept and becomes an approximation. Imagine two observers moving relative to one another. Each observer carries an accurate clock. They can meet, separate, and later compare their clocks. The clocks can disagree about the amount of elapsed time. Neither clock is wrong. There is no hidden master clock that can decide which one has the real time. The disagreement is built into space-time itself. This is one of the reasons relativity is so difficult to reconcile with intuition. We are used to thinking of space as something that exists and time as something that flows, while objects simply move through both. Einstein's theory replaces that picture with space-time, where the geometry itself is affected by motion and gravity. Time is not something that happens independently of the geometry. The geometry determines what different clocks can measure. The distinction between coordinate time and proper time becomes important here. Coordinate time is something we can introduce to describe events using a chosen coordinate system. Proper time is what a clock actually measures along its own world line. Those two concepts can coincide in convenient situations, but they do not have to. The proper time accumulated by a clock depends on its path through space-time. In that sense, your own clock does not need permission from the rest of the universe to determine how much time you have experienced. It measures the duration along your trajectory. Another observer has a different trajectory and can therefore accumulate a different amount of proper time between the same broad set of events. This is why the famous twin scenario is not really about one twin somehow traveling into a different version of time. The twins simply follow different paths. The geometry of spacetime assigns different proper times to those paths. Scott Kelly's time in orbit provides a real-world example of this principle. His accumulated difference relative to his Earthbound twin was tiny, around 5 milliseconds over approximately 340 days, but the physical meaning is enormous. If you could somehow magnify that difference, it would not be a measurement error. It would be a direct demonstration that elapsed time is path-dependent. Once you understand that, the next question becomes unavoidable. If there is no universal amount of elapsed time, what does it mean to say that the universe itself has an age? Cosmology commonly describes the universe as approximately 13.8 billion years old. That number is extremely useful. But what does old mean in a relativistic universe? The answer depends on the cosmological model and the way cosmic time is defined. Cosmologists can construct a useful time coordinate associated with observers who move with the large-scale expansion of the universe. That gives us a common cosmic timescale for describing the evolution of the universe as a whole. But that cosmic time is a feature of the cosmological model, not a universal Newtonian clock existing independently of spacetime. This distinction becomes particularly important when discussing the beginning of the universe. People often imagine the Big Bang as an explosion that happened at one location in pre-existing space, followed by the universe expanding outward into an empty environment. That is not what the standard cosmological picture says. The expansion refers to the evolution of spacetime itself. There is no obvious external space into which the universe is expanding, and asking what happened before the beginning can become problematic depending on what theory of the beginning you are using. If time itself is part of the physical structure being described, then the question, what happened before time began, may not be analogous to ordinary questions about earlier events. It may be more like asking, what is north of the North Pole? The difficulty is not that the answer is hidden somewhere. The coordinate you are trying to extend may simply stop having the meaning you expect. But this is exactly where we encounter a major limitation. The standard cosmological model does not give us a complete quantum theory of the beginning. General relativity can describe an expanding universe and can be extrapolated backward or to extremely early conditions, but eventually quantum effects should become important. At that point, our classical description of spacetime is expected to become inadequate. This is one reason the problem of time and quantum gravity matters so much. The question is not merely philosophical. If the geometry of spacetime itself becomes quantum, then the external time parameter used by ordinary quantum mechanics becomes difficult to justify. The Wheeler-DeWitt equation is famous because it exposes this tension so dramatically. In ordinary quantum mechanics, the Schrödinger equation tells us how a quantum state changes with respect to time. But when the gravitational field itself becomes part of the quantum state, the corresponding equation can be written without the ordinary time parameter. The universe is represented by a state satisfying a constraint rather than by a state evolving against an external clock. This is sometimes described as a frozen universe, but that phrase can be misleading. The absence of an external time parameter does not necessarily mean that nothing can ever change. Yeah, it means that change has to be described differently. This is where relational time becomes useful. Suppose you have two quantum subsystems, one that behaves like a clock and another that behaves like the system you want to observe. Instead of asking how the entire universe changes relative to some external time, you ask how the state of one subsystem correlates with the state of the other. If the clock subsystem has one state, the other subsystem is found in a corresponding state. If the clock has another state, the other subsystem is found in another state. To an observer inside the universe, those correlations can look like ordinary time evolution, even if the global description does not contain an external time variable. The Page-Wouters mechanism is an example of this general idea. The universe as a whole can be described as a stationary quantum state, while an internal observer sees evolution because the observer becomes correlated with a clock subsystem. That is a strange possibility because it suggests that the experience of time could be an internal phenomenon rather than a feature imposed from outside. The universe does not have to be running on an external clock for its internal parts to experience sequences of events. The entangled photon experiment associated with this idea is important for exactly that reason. One photon can act as a clock, while another represents the system whose evolution is being described. From an external perspective, the combined state can be static. From the internal perspective, defined by correlations with the clock, the system can appear to evolve. Again, this does not prove that the universe is literally frozen or that time does not exist. It demonstrates that a notion resembling time evolution can arise from correlations within a larger quantum state. Now consider what that would mean for an observer. You are not standing outside the universe looking at it. You are part of it. Your body is a physical system. Your brain is a physical system. Your memories are physical states. Your perception of sequence comes from physical processes happening in a particular order relative to other processes. If relational time is the correct way to think about fundamental physics, then your experience of time is not something imposed on you by a universal cosmic clock. It emerges from the correlations among the physical systems that make up you and the environment around you. That may sound abstract until you connect it to memory. A memory is not simply a thought floating around in your mind. It corresponds to a physical state of a physical system. Your brain is different after an event because information about that event has been encoded in its physical structure. The present state contains a record of something that happened earlier. That asymmetry is important. You have records of yesterday because physical interactions have left traces in the present. You do not have records of tomorrow because future events have not yet produced those traces. This is where the arrow of time becomes connected to information. Entropy is not simply a synonym for messiness. It is a statistical measure related to the number of microscopic configurations compatible with a macroscopic state. A low entropy state corresponds to a much more restricted set of microscopic possibilities. A high entropy state corresponds to many more possibilities. If the universe begins in a highly special low entropy state, then ordinary statistical evolution naturally tends towards states compatible with vastly more microscopic configurations. That gives us a direction from lower entropy to higher entropy. But why should the universe have started in a low entropy state? This is one of the deepest problems behind the thermodynamic arrow. The laws of statistical mechanics can explain why entropy is overwhelmingly likely to increase from a special low entropy condition, but they do not automatically explain why that special condition existed. The directionality we experience may therefore be inherited from an initial boundary condition rather than being directly written into the microscopic equations. That distinction matters because it means the arrow might not be a fundamental law in the same way that the laws governing quantum transitions are. Imagine a microscopic process whose equations work equally well forward and backward. If you prepare the system in an extremely special state, the overwhelming majority of possible evolutions will move towards states with greater entropy. An observer embedded in that evolution will identify one direction as the future. The equations themselves did not have to say this way is future. The statistical structure of the initial state created the asymmetry. This is why the beginning of the universe becomes so important. The universe's low entropy initial condition is sometimes described as the past hypothesis. It provides a boundary condition that can explain why entropy has increased from the early universe to the present. But the hypothesis itself is not an explanation of why the boundary condition exists. It simply identifies the condition needed to account for the arrow. The deeper question remains open. And there is a subtle consequence. If the arrow of time is tied to entropy, then the direction of time is closely connected to the existence of records. To create a record, a physical system must interact with its environment. That interaction generally increases entropy somewhere. Landauer's principle gives a quantitative connection between information processing and thermodynamics. Erasing one bit of information has a minimum energy cost proportional to temperature. The physical world, therefore, does not allow information to be manipulated without consequences. This does not mean that every thought or memory has a fixed energy price exactly equal to the Landauer bound. The bound applies to logically irreversible operations under the relevant thermodynamic conditions, and real systems usually dissipate much more energy. But the fundamental point remains: information is physical. A bit is represented by a physical state, and changing or erasing that state is a physical process. The microscopic double-well experiment makes this principle concrete. The system can represent a bit using two possible physical states, and researchers can manipulate it and erase the stored information. The measured heat dissipation can approach the theoretical minimum. The closer the experiment gets to the bound, the more clearly the abstract concept of information becomes tied to the physical laws of thermodynamics. That has a strange implication for time. A physical record is effectively a correlation between a present state and a previous event. The record does not contain the past itself. It contains information that allows the present to constrain what must have happened before. A photograph does not contain the event that happened in front of the camera. It contains a physical pattern created by light from that event. A memory does not contain yesterday. It contains a physical configuration produced by interactions that happened yesterday. This distinction is essential because it suggests that the past is not something sitting somewhere behind us in a physical storage location. The past is represented by present records. The universe does not need to preserve an invisible copy of every previous moment. It only needs physical correlations that encode information about previous states. The future is different because there are not yet corresponding records. That is one possible reason the future feels open while the past feels fixed. The past has left traces. The future has not. From the standpoint of thermodynamics and information, this asymmetry can be physically meaningful even if the fundamental equations do not contain a simple forward arrow. But quantum mechanics complicates the story again. A quantum state does not necessarily assign a definite classical history to a system. Before measurement, a system can be described as a superposition of possibilities. Different paths can interfere. What we call a particular past can sometimes emerge only after interactions with the environment produce stable records. This is related to decoherence, where a quantum system becomes entangled with its environment, and interference between different macroscopic alternatives becomes effectively inaccessible. Decoherence does not solve every philosophical question about measurement, but it helps explain why the everyday world looks classical, even though its underlying components obey quantum mechanics. The environment continually interacts with physical systems. Information about different possible states spreads into the surroundings. Once that information becomes distributed across many degrees of freedom, recovering the original quantum coherence becomes extraordinarily difficult. The world then acquires stable records. This is another place where time and information meet. The environment effectively becomes a witness. A quantum event can leave traces in many parts of its surroundings, and those redundant records are what allow classical facts to become robust. The past becomes increasingly difficult to erase because information about it has been copied into the environment. But notice the subtlety. The fundamental quantum equations can remain reversible while the macroscopic process appears irreversible. If you had complete microscopic control over every degree of freedom, the underlying dynamics could in principle be reversed, but in practice, the information is distributed across an enormous number of particles. Reconstructing the exact state needed to reverse the process becomes effectively impossible. The irreversibility is therefore statistical and informational rather than necessarily built into the basic microscopic equation. This is one reason why a broken glass is such a useful example. The microscopic laws do not contain a simple instruction saying glass may break but never unbreak. The particles obey physical rules that can be written in both directions. Yet once the glass shatters, the information about the exact arrangement of every fragment becomes dispersed into the environment. Air molecules move, vibrations propagate through the floor, heat spreads, tiny interactions occur everywhere. To reverse the process, you would have to coordinate an enormous number of microscopic variables with extraordinary precision. The reverse event is not forbidden by the equations in the simple classical picture, but it is overwhelmingly improbable. The same reasoning applies to memory. Your brain does not have to contain a literal movie of the past. Instead, physical changes encode information about previous interactions. Those changes are themselves embedded in a larger thermodynamic process. You remember because the present contains records. The arrow of time is therefore deeply intertwined with the physical creation and persistence of records. This is also why the quantum clock experiment is so interesting. The clock can tick through a physical process, but extracting information about those ticks can have a much larger energetic cost than the ticking process itself. That difference separates two concepts that we usually treat as identical: time passing and knowing that time passed. A physical event can happen without anybody observing it. But if you want to use the event as a measurement, information about it must become accessible. The measuring apparatus has to interact with the system. The information has to be stored somewhere. The storage has physical consequences. In the quantum regime, the distinction becomes impossible to ignore because the measurement interaction can also modify the system. The quantum Zeno effect provides a striking example. If a quantum system is repeatedly measured at sufficiently short intervals, its evolution between states can be inhibited. The more frequently the system is checked, the more strongly the transition can be suppressed under the conditions required for the effect. The measurement is not merely reporting the system's state, it becomes part of the dynamics. This gives us a strange chain of relationships. A clock requires a physical change. A measurement requires an interaction. Information requires a physical representation. Erasure has a thermodynamic cost. Repeated measurement can modify quantum evolution, and the arrow of time is associated with the accumulation of physical records. None of these facts by itself explains time, but together they suggest that the familiar concept of time is inseparable from the physical processes that allow systems to change and record those changes. There is another issue hiding underneath all of this. What exactly does it mean for an event to happen? In ordinary language, we assume that an event has a definite place in a timeline. First it happens, then something else happens. But quantum causal order experiments challenge that assumption at the fundamental level. In a classical circuit, imagine two operations, A and B. If A modifies a system before B acts on it, then the output can differ from the situation in which B happens first. The order is definite. In a quantum process, however, the system can be arranged so that the two orders exist in a superposition. The causal relationship itself becomes indefinite. The quantum switch is one way of describing such a setup. A control system determines whether one operation occurs before another, but the control can itself be placed in a quantum superposition. The resulting process cannot always be described as simply A happened first or B happened first. Both causal orders contribute to the quantum state. This is not just a bizarre trick with labels. Researchers have demonstrated advantages associated with indefinite causal order for certain information processing tasks. That means the phenomenon can have operational consequences. The order of operations is not merely something we are confused about. The quantum structure of the process can actually depend on the indefinite order. The deeper implication is that causality itself may be more fundamental than time, or perhaps time and causality emerge together from a deeper structure. If causal order can become indefinite, then a fundamental theory of reality cannot necessarily assume that every pair of events already has a fixed temporal relationship. This is especially relevant to quantum gravity because gravity determines the geometry of spacetime and therefore determines the causal structure that tells us which events can influence which others. If spacetime itself becomes quantum, then the causal structure may become quantum as well. You could no longer assume that the geometry is a fixed background on which quantum processes occur. The geometry would have to participate in the quantum description. That is precisely the type of situation where the ordinary concept of time begins to fail. In ordinary quantum mechanics, you can say that a system evolves over time because the background clock is assumed. In general relativity, the geometry of spacetime is dynamic. In quantum gravity, both the matter and the geometry may need to be treated quantum mechanically. Then what is the clock measuring? What defines the sequence of events? What does it mean for one state to come before another if the geometry that defines before is itself uncertain? This is not just a philosophical puzzle. It affects how a future theory of quantum gravity must be formulated. If the theory requires a fixed external time parameter, then it risks contradicting the relational structure of general relativity. If it removes time completely, it has to explain why observers experience a consistent temporal sequence. The theory must somehow reproduce the ordinary world where clocks agree approximately, entropy increases, causes precede effects, and memories point toward the past. The challenge is to get all of that behavior from a deeper description that may not contain time in the familiar form. One possibility is that time emerges from entanglement. In quantum theory, entanglement describes correlations between systems that cannot be reduced to independent states. Some approaches to quantum gravity suggest that space-time geometry may itself be related to quantum entanglement. If the structure of space can emerge from relationships among quantum degrees of freedom, then perhaps the structure of time can emerge through related mechanisms. But this is where we have to be careful, because there is no single experimentally confirmed theory that establishes this. These ideas are active research directions, not settled facts. The experimental results we have are constraints and clues. They tell us what a successful theory must reproduce. They do not yet tell us the final mechanism. The same caution applies to the idea that time emerges from information. Information clearly has physical consequences, and information processing is constrained by thermodynamics. But that does not automatically mean information is the fundamental substance from which time is constructed. It is possible that information and time are both emergent consequences of an even deeper theory. The most honest position is therefore also the most interesting one. We have several pieces of evidence pointing toward relationships among time, entropy, information, quantum measurement, causality, and gravity, but we do not yet know the complete structure connecting them. The precision of modern clocks makes this uncertainty more useful because it turns vague philosophical questions into measurable experiments. Suppose a fundamental constant really did drift over time. An ordinary clock would not notice, but a clock based on an extremely precise atomic transition might. If two different types of clocks respond differently to a change in a fundamental constant, their ratio could reveal the drift. You would not be asking whether time itself changed. You would be asking whether the physical processes used to define time remained governed by exactly the same constants. This is an important conceptual distinction because a change in a clock's frequency does not automatically mean that time itself has changed. If the atom's transition frequency changes because a fundamental constant changes, the clock would tick differently even if some deeper notion of duration remained unchanged. That is why comparisons between different clock technologies matter. Researchers are not simply watching one clock and asking whether it feels normal. They are comparing physical processes that depend differently on the laws of physics. The more independent physical processes agree, the stronger the case that the underlying time standard is stable. If they begin to disagree in a correlated way, that could indicate new physics. This is one reason the idea of a nuclear clock is so important. Atomic clocks rely on electronic transitions, while a nuclear clock would rely on a transition within the nucleus. The different physical environment can make the system sensitive to different possible variations in fundamental constants. Comparing a nuclear clock against an atomic clock could therefore provide a powerful test of whether the parameters of physics have remained stable. If a drift were found, the result would be enormous. It would not necessarily mean that time itself is changing. It would mean that quantities we have treated as fixed components of physical law may have a deeper dependence on the state or history of the universe. That would force us to rethink what we mean by a constant. And that brings us back to the strange relationship between laws and time. We usually imagine the laws of physics as eternal rules. The universe changes, but the rules do not. A ball falls today according to the same gravitational law it followed yesterday. An electron behaves according to the same quantum rules now as it did billions of years ago. But if precision clocks ever detected a systematic change in a fundamental constant, then the laws would appear to evolve with cosmic time. The question would then become, What law governs the evolution of the laws? That sounds like a joke, but it is a genuine conceptual problem. If the constants vary, there must be some deeper mechanism determining their values. That mechanism would itself have to be described by some theory. If its behavior changes, another layer of explanation would be required. Physics normally avoids this infinite regress by treating the constants as fixed inputs. A measurement showing that they are not fixed would force us to replace those inputs with dynamical fields or deeper principles. This is another reason why clocks are such powerful tools. They are not just instruments for tracking human schedules. They are controlled physical systems that can test the stability of the universe's rules. The experiments also reveal something important about scale. At human scale, time appears smooth. Your watch's second hand moves continuously. You experience a continuous flow from one moment to the next. But at microscopic scales, physical processes are described through quantum states and transitions. There is no requirement that every system behave like a tiny mechanical clock with a continuously moving hand. Some processes are better described in terms of discrete energy levels and probability amplitudes. Does that mean time itself is quantized? Not necessarily. Quantum mechanics quantizes many physical observables, but it does not automatically imply that time must come in discrete chunks. Standard quantum theory treats time differently from observables such as position or momentum. Whether a fundamental theory of quantum gravity will preserve this distinction is unknown. There are approaches in which space-time itself could have a discrete structure at extremely small scales, but this remains theoretical. No experiment described here establishes that time is made of tiny, indivisible units. What the experiments do show is that our ordinary continuous intuition is not guaranteed to remain the right description at every scale. That distinction matters because popular explanations often jump from quantum to everything is discrete. Physics is more complicated. Quantum mechanics allows continuous variables and continuous evolution in many contexts. What changes is the structure of the state space, the measurement process, and the probabilities associated with different outcomes. The problem of time is therefore not solved by simply declaring that time is quantized. The deeper challenge is to understand whether a meaningful temporal parameter exists at the level where space-time itself must be treated quantum mechanically. There is another route into the problem through black holes. A black hole is not simply a very dense object sitting in ordinary space. Its event horizon is a causal boundary. Once something crosses the horizon, it cannot send a signal back out to a distant observer, according to classical general relativity. The geometry determines which future-directed paths are possible. But Hawking radiation means that black holes are not completely eternal. They can radiate and lose mass. If the black hole eventually evaporates, the information about what fell in has to be accounted for somehow if quantum mechanics remains unitary. This is where the phrase information loss becomes dangerous, because it can sound like information simply disappears from the universe in the ordinary sense. The actual problem is more precise. Quantum theory says that the complete state of a closed system evolves in a way that preserves information. A black hole formed from a highly specific quantum state should, therefore, in principle, retain the information needed to distinguish that state from another. But Hawking's original semi-classical calculation suggests radiation that appears thermal and insensitive to the detailed information about what formed the black hole. If the radiation is truly thermal and the black hole disappears, the final state would seem unable to reconstruct the original information. That creates a conflict between quantum mechanics and semi-classical gravity. The reason this matters for time is that unitary quantum evolution provides a relationship between earlier and later states. If information can be destroyed, then the mapping from past to future is no longer one-to-one. The future would not contain enough information to reconstruct the past. The meaning of a physical history would be fundamentally altered. Modern ideas about black holes and quantum gravity suggest that the information may not actually be destroyed, but the mechanism by which it is preserved is one of the deepest questions in the field. Concepts such as holography, entanglement, and black hole entropy have transformed the discussion, but they have not turned the problem into something simple. The entropy of a black hole is itself extraordinary because it scales with the area of the event horizon rather than the volume inside it. That fact helped motivate the holographic principle, which suggests that the information content of a region of space may be encoded on a lower dimensional boundary. Again, this is not proof that the universe is literally a hologram in the popular sense. It is a statement about how gravitational systems appear to organize information. If information is more fundamental than our ordinary picture of spacetime suggests, then the relationship between information and time could be deeper than we currently understand. Perhaps what we call temporal evolution is partly the process by which information becomes redistributed among physical degrees of freedom. Perhaps the arrow of time is the direction in which information becomes increasingly encoded in correlations that are difficult to reverse, or perhaps that is only one layer of a much deeper explanation. There is also an important distinction between reversible computation and irreversible computation. A logically reversible operation can, in principle, be undone without necessarily erasing information. An irreversible operation maps multiple possible input states into one output state, so information about the original input is lost unless it is stored somewhere else. Landauer's principle applies to this logical irreversibility. This tells us something subtle about the arrow of time. Thermodynamic costs are associated not with computation in general, but with particular transformations that erase distinctions between possible states. That means information itself is not necessarily expensive. It is the irreversible destruction of information that carries a minimum thermodynamic cost. A reversible physical process can, in principle, preserve information without the same unavoidable dissipation. This becomes relevant to quantum computing, where quantum evolution is generally reversible until measurement or other irreversible operations are introduced. A quantum computer can manipulate superpositions and entanglement while preserving information through unitary evolution. But eventually, if you want a classical answer, you need to extract information from the quantum system. Measurement and reset processes then become physically important. The quantum clock experiment can be viewed through a similar lens. The clock's physical dynamics can be comparatively efficient, but obtaining a classical record of those dynamics can require energy. This reinforces the distinction between a system undergoing evolution and an observer acquiring information about that evolution. And that distinction may be one of the reasons our subjective experience of time is so strongly connected to memory. Consciousness does not necessarily need a metaphysical flow of time to experience sequence. A physical system with states that encode previous states can generate a coherent internal ordering. The brain is continuously receiving information, integrating it, and updating its physical state. The current state contains traces of previous interactions. That creates a physical basis for a direction from remembered states toward currently experienced states. But again, this does not explain why the universe began in the condition that allows memory and entropy to develop in this direction. It moves the question from why does time flow to why did the universe begin in a state that supports this arrow? That is a much harder question. It is also why the early universe matters so much. The early universe was extremely hot and dense, but high temperature does not automatically mean high gravitational entropy. The special nature of the early gravitational state is one of the reasons the low entropy beginning remains a serious issue. The universe began in a highly constrained gravitational configuration, and that may be what ultimately allowed structures such as stars, galaxies, and planets to form while entropy increased overall. Stars are a good example of how local order can arise while total entropy increases. A star forms from matter collapsing under gravity into a more structured configuration, but the process releases energy and increases entropy elsewhere. The emergence of organized structures does not violate the second law because entropy is a global statistical quantity. Local decreases can happen as long as they are compensated by larger increases elsewhere. This is another reason entropy equals disorder is an incomplete explanation. The universe can become more structured in some regions while overall entropy increases. The arrow of time is not simply the universe becoming messier. It is about the statistical distribution of microscopic states and the number of configurations compatible with macroscopic conditions. The same principle explains why life does not violate thermodynamics. Living systems maintain highly organized internal states by exchanging energy and matter with their environments. They consume low entropy energy and release higher entropy waste and heat. The local organization of life exists within a larger thermodynamic process. From this perspective, the existence of observers does not require a special violation of the arrow of time. Observers are physical systems operating within the same thermodynamic framework. We remember the past because our physical states contain records. We anticipate the future because we construct models based on those records. The direction of our psychological time is therefore closely connected to the physical arrow. But psychological time can also be misleading. Your perception of duration is not perfectly uniform. A minute can feel extremely long in one situation and almost disappear in another. That does not mean physical time changed. It means the brain's representation of temporal duration depends on processing and memory. The subjective experience of time is therefore another layer on top of physical time, not necessarily a direct window into its fundamental nature. This is important because the word time is doing too much work. There is physical duration measured by clocks. There is coordinate time in equations. There is thermodynamic time associated with entropy. There is psychological time associated with perception. There is cosmological time used to describe the evolution of the universe. There is proper time along world lines. There is relational time in quantum gravity proposals. These concepts overlap, but they are not identical. The fact that one word describes all of them may be part of the reason the subject feels mysterious. We intuitively assume that all these meanings refer to one underlying thing. Physics has not yet demonstrated that they do. The most powerful experiments therefore do not ask a vague question like, is time real? They ask much narrower questions. Do clocks at different gravitational potentials run at different rates? Yes. Does motion change elapsed proper time? Yes. Can gravitational time dilation be detected over millimeter scales? Yes. Can quantum causal order become indefinite? Yes, under appropriate conditions. Does measurement have a thermodynamic cost? Yes. Can repeated measurement alter quantum evolution? Yes. Can a quantum system provide an internal reference for temporal evolution without an external clock? Experiments have demonstrated important pieces of this idea. Does the quantum description of the universe naturally contain an external time parameter? Not necessarily. Does cosmology currently give a completely settled history of cosmic expansion? No, because there are unresolved tensions in measurements and models. Each answer is specific. None is the final answer to what time is. That may actually be the most important lesson from the entire story. Science does not become more powerful by turning every strange result into a grand conclusion. The strength of these experiments comes from exactly how limited their claims are. A clock that measures a gravitational difference tells us about gravitational time dilation. A quantum switch tells us about causal order. A Landauer experiment tells us about the thermodynamic cost of erasure. A quantum Zeno experiment tells us about measurement and evolution. A nuclear clock tests the stability of physical constants. A cosmological observation tests the model of cosmic expansion. When you connect these results, you can see a pattern, but you should not pretend that the pattern is already a finished theory. The pattern is that time repeatedly refuses to behave like an independent universal background. It changes with gravity, it changes with motion, its direction is connected to entropy, its measurable records are tied to information, its quantum description can depend on measurement, its causal ordering can become indefinite, its ordinary external parameter can disappear from a description of the entire universe. And the instruments we use to measure it are themselves physical systems governed by the same laws we are trying to understand. That last point may be the strangest of all. When physicists build a clock, they are not creating an independent reference outside reality. They are selecting one physical process and using it to compare another physical process. The clock is part of the universe. Its behavior depends on the same space-time geometry, quantum laws, and fundamental constants as everything else. There is no privileged instrument sitting outside the system and measuring reality from a neutral position. In principle, Every measurement is a relationship between physical systems. That means the ultimate question of time may not be, what does time do? It may be what relationships among physical systems generate the quantity we call time. This is a very different question. If the answer is relational, then there may be no single object called time. There may only be networks of correlations. One system changes relative to another. A third system records the relationship. A fourth system interacts with that record. From inside the network, an ordered sequence emerges. The universe does not need a separate temporal substance any more than a map needs an invisible substance called distance. Distance describes relationships between positions. Time could describe relationships between physical states. But even this picture leaves a problem. Relationships require something to be related. If time emerges from correlations between physical systems, what is the underlying structure from which those systems themselves emerge? If space-time emerges from quantum entanglement, what is entanglement a property of? If geometry emerges from information, what physical degrees of freedom carry that information? If the arrow of time emerges from a low-entropy initial condition, why did that condition exist? Every proposed explanation seems to push the mystery one level deeper. That does not make the research pointless. It means fundamental physics often progresses by identifying exactly where an old concept stops working. Newtonian time worked extraordinarily well until high velocities and strong gravitational fields exposed its limitations. Classical spacetime works extraordinarily well until quantum effects become unavoidable. Standard quantum mechanics works extraordinarily well until you ask what happens when the clock and the spacetime geometry must themselves be quantum. The unresolved edges are where the next theory has to operate, and that is why experiments on time are becoming more precise rather than less important. The goal is not simply to build a clock that loses 1 second over an unimaginably long period. The goal is to build a physical system sensitive enough to reveal a deviation from the theories we already have. A tiny discrepancy can be more valuable than a perfect confirmation because a discrepancy tells us where the current framework breaks. ACES is one example of this philosophy. By comparing precise clocks in space with clocks on Earth, researchers can test relativistic effects and search for possible deviations. The experiment turns the entire planet into part of the apparatus because Earth's gravitational field provides the environment in which the clocks operate. The International Space Station becomes not just a place to conduct experiments, but a different gravitational and kinematic reference point. The same logic applies to clocks on Earth. A clock at one elevation and another at a different elevation experience slightly different gravitational potentials. The difference can be measured. If clocks become accurate enough, altitude becomes something that can be inferred from gravitational time dilation itself. That means a sufficiently precise clock is effectively a gravitational sensor. This is one of the reasons optical clocks and other advanced timekeeping technologies could become useful for geodesy. Instead of measuring elevation only with traditional surveying methods, researchers can use gravitational redshift as a measure of differences in gravitational potential. The clock is no longer just telling you the time, it is telling you something about the geometry of the gravitational field. That is a remarkable transformation. Timekeeping becomes a way of measuring space, and relativity predicts this because space and time are not independent quantities. The geometry of space-time determines how clocks behave. If you can measure the clock precisely enough, you can infer information about the geometry. This leads to a strange conceptual loop. We use geometry to explain clocks. We use clocks to measure geometry, we use clocks to test the theory of gravity, and then we ask whether the geometry itself is fundamental or emergent. The instrument used to investigate spacetime becomes part of the evidence about what spacetime actually is. The same thing happens with quantum clocks. We use a quantum process to define a temporal reference, but the process itself is subject to quantum uncertainty. If the clock is in a superposition of states, what does it mean to ask what time it reads? If different components of the clock's state experience different gravitational rates, the clock can become entangled with the system it is measuring. The clean separation between clock and system begins to disappear. This is exactly the kind of issue that ordinary physics avoids by assuming the clock is classical. A classical clock is treated as an external reference whose own state can be ignored, but the universe has no truly external classical clock. Every clock is ultimately a physical quantum system. The approximation works because ordinary clocks are macroscopic and decohered, but at fundamental scales, the distinction may fail. Once it fails, the question becomes unavoidable. Can time itself be a quantum observable? Standard quantum mechanics says time is usually a parameter rather than an observable. But if a clock is treated as a quantum system, then the time it indicates can become correlated with its quantum state. There are approaches to quantum time that attempt to describe this explicitly, including quantum clocks, relational observables, and frameworks where time emerges from internal degrees of freedom. Again, none has been experimentally established as the final theory. But the experiments are gradually forcing us toward the question. There is another subtle problem. Clocks require periodicity or some repeatable process, but not every physical process is periodic. The universe does not contain a single universal oscillator that everything else synchronizes to. We choose stable transitions because they provide reliable references. A second is defined by a particular atomic transition because that process can be reproduced under controlled conditions. That means our unit of time is ultimately anchored to a physical property of matter. If matter behaved differently, our clock would behave differently. If fundamental constants changed, the transition frequency could change. If gravitational potential changed, the clock rate would change. If the clock moved rapidly, the elapsed proper time would differ. If the clock became a quantum system, the measurement process would matter. At no point do we encounter an independent substance called time. We encounter physical systems and relationships. This does not prove that time is emergent. It simply shows that every operational measurement of time is physical. That distinction is important because physics often defines quantities operationally. We know what it means to measure a length because we can compare it against a standard. We know what it means to measure energy because we can observe its effects and relate it to physical processes. We know what it means to measure time because we compare physical processes. The operational definition is enough for science to make predictions, but the metaphysical question of what the quantity really is can remain open. Maybe that is all there is to the concept. Perhaps asking what time really is beyond its physical relationships is like asking what the number 3 is made of. The number is not a substance. It is an abstract structure describing relationships. Time might be similar. But physics has an additional complication because time appears in the fundamental equations themselves. It is not merely a label we attach after the fact. It determines how states evolve in ordinary formulations. That makes the disappearance of time from the Wheeler-DeWitt equation so significant. If the deepest equation does not need the parameter that ordinary physics uses to describe evolution, then perhaps the parameter is not fundamental. This is where the phrase emergent time becomes useful. An emergent quantity is not fake. Temperature is real. Pressure is real. Sound is real. They emerge from collective behavior. A temperature can burn you even though there is no individual molecule with temperature in isolation. A sound wave can shatter glass even though the individual molecules do not contain a little sound inside them. Emergent does not mean imaginary. So if time emerges, that would not make your life unreal or your clock useless. It would mean that the familiar temporal structure is a large-scale property of a deeper physical system. The challenge is finding a mathematical theory that produces ordinary time as an approximation and also reproduces relativity, quantum mechanics, thermodynamics, and the observed universe. That is an enormous constraint. A successful theory cannot simply remove time and declare victory. It has to explain why we recover the time measured by atomic clocks, why gravitational time dilation works, why GPS requires relativistic corrections, why entropy increases, why memories point toward the past, why quantum systems evolve according to known laws, and why causal influences obey the observed structure of space-time. It must explain both the absence and the appearance of time. That is the real difficulty. The same issue appears in cosmology. If the universe is described by a quantum state without an external time parameter, then Cosmic evolution must somehow emerge internally. The cosmological arrow of time must also be explained. The low entropy early universe must be accounted for. The observed expansion must be recovered. Dark energy and the Hubble tension must fit within the framework or reveal where it needs modification. One theory has to connect all of these things without contradicting the experiments that already work. That is why there is no simple answer yet. And perhaps the most disturbing possibility is not that time disappears, but that there is no single underlying answer. Maybe the concept of time has several layers that emerge at different scales. At the quantum level, there may be correlations in causal structures. At the gravitational level, geometry determines proper time. At the thermodynamic level, entropy creates an arrow. At the biological level, memory and metabolism create subjective duration. At the cosmological level, expansion provides a useful global time coordinate. These layers could all be manifestations of one deeper structure, but the structure might not resemble time as we experience it. This would explain why different areas of physics seem to give different answers. They are not necessarily disagreeing. They may be describing different limits of the same underlying theory. The problem is that we do not yet know what that theory is. For now, the clocks keep ticking. The cesium transition continues to define the second. The aluminum ion can be interrogated with extraordinary precision. The clocks on Earth and in orbit can be compared. A clock can detect the difference caused by a millimeter of gravitational potential. A quantum dot can produce ticks through electron transitions. A quantum system can respond differently depending on whether and how it is measured. A quantum process can contain indefinite causal order. A universe-wide quantum equation can be written without the familiar external time variable. And despite all of these developments, your ordinary experience remains stubbornly familiar. Morning follows night. Your memories accumulate. Objects move. People age. Events happen. You make plans for things that have not happened yet and remember things that have. The macroscopic world still looks like a universe moving through a single direction of time. That consistency is not evidence that the deeper problem has disappeared. It is evidence that whatever the underlying description is, it has to reproduce the world we experience. The mystery is therefore not whether time exists in daily life. It obviously does in the operational sense that clocks measure reproducible durations and physical processes occur in ordered relationships. The mystery is whether the familiar temporal structure is fundamental or emergent. And the answer may depend on what happens when the next generation of experiments pushes clocks beyond their current limits. If two fundamentally different types of clocks were ever found to drift relative to each other in a way that cannot be explained by known physics, that would be an enormous clue. If a quantum clock in a superposition of gravitational potentials behaved in a way that cannot be captured by current theory, that would be another. If a precision experiment revealed a deviation in the predicted gravitational redshift, the structure of spacetime itself would need to be reconsidered. If a controlled experiment revealed new violations of expected symmetries, we would have another piece of the puzzle. The goal is not to prove that time is weird. We already know it is weird. The goal is to discover exactly how weird it is, because every successful measurement removes another layer of approximation. Newton's absolute time was replaced by relativistic proper time. Classical determinism was complicated by quantum measurement. A fixed causal order was shown not to be universally required in quantum processes. Thermodynamic irreversibility emerged as a statistical phenomenon rather than a simple microscopic rule. Information became recognized as a physical quantity with thermodynamic consequences. And quantum gravity continues to challenge the assumption that spacetime and time can simply be treated as fixed backgrounds. The story is not finished. If anything, the most precise clocks ever built are telling us that the question has only become sharper. We began with a simple assumption. Time is something that flows, clocks measure it, and everything in the universe shares the same underlying passage. Relativity removed the universal flow. Thermodynamics gave us an arrow without a simple microscopic direction. Quantum mechanics made measurement and causality stranger. Information theory connected records to physical entropy. Quantum gravity removed the external clock from some fundamental formulations. Cosmology showed that our description of the universe's history is still being tested. And precision clocks are now sensitive enough to probe differences that would have been completely invisible to earlier generations of physicists. So the question is no longer whether clocks can measure time accurately. They can. The question is whether the thing they measure is fundamental. If it is, we still need to understand why it behaves relationally, why gravity changes its rate, why quantum theory treats it differently from other observables, and why the arrow of time is so closely associated with entropy and information. If it is not fundamental, we need to explain how an apparently universal temporal world emerges from something deeper, and why every observer inside that world experiences such a consistent sequence of events. Either way, the old picture is gone. There is no universal cosmic second ticking independently of matter and gravity. There is no single present shared by every observer. There is no simple microscopic explanation for why the future feels different from the past. There is no guarantee that causal order is always fixed at the quantum level. And there is no requirement in the quantum description of the universe that an external time parameter must appear in the way we expect. Yet somehow from all of this, the world we live in emerges. You wake up, check a clock, and know roughly when it is. You remember yesterday. You plan tomorrow. You watch a physical system change and call that duration. Every part of the experience feels obvious because your brain, body, environment, and clocks are all operating within the same macroscopic regime. But underneath that familiar experience is a much stranger physical reality. A clock does not detect time as though time were a fluid flowing through it. It undergoes a physical process. A second is defined through that process. Different physical conditions alter the process. Other physical systems provide comparisons. Information about the process must be physically encoded if you want to read it. The reading itself can have thermodynamic consequences. At the quantum level, the act of observing can alter evolution. At the gravitational level, the geometry changes the amount of proper time accumulated. At the cosmological level, the entire history of the universe is reconstructed using models whose parameters are still being tested. And at the deepest theoretical level, the ordinary time variable may not even be present. That is why the title of this story is more accurate if you understand disturbing in a very specific way. The results are not disturbing because a laboratory discovered some catastrophic anomaly. They are disturbing because every increase in precision makes our common sense picture less fundamental. The universe does not appear to contain one universal clock sitting behind everything else. Instead, it contains physical systems that change relative to one another, interact, record information, and follow paths through a dynamic geometry. The time you experience may be the large-scale result of all of those relationships. And if that is true, then time may be less like a river and more like a structure created by the universe's own internal relationships. But even that metaphor has to be handled carefully because the moment we call time a structure, we are already imagining it as something that exists independently. The deeper theory may not contain anything that resembles our everyday concept at all. It may contain quantum states, correlations, constraints, fields, geometry, and information, with time appearing only when a particular subsystem is used as a reference for another. That would mean that asking when did the universe begin is not always as simple as it sounds. The answer depends on the physical time coordinate being used and the theory that defines it. Asking what happened before the universe may similarly depend on whether before remains meaningful beyond the regime where our current description applies. We are used to thinking that every event must have another event before it. But that assumption itself may be a feature of the temporal structure that emerges inside the universe. At the fundamental level, the question could be malformed, and that is perhaps the most unsettling possibility of all. The universe may not be something that exists inside time. Time may be something that exists inside the universe. The distinction is subtle, but enormous. If time is fundamental, then the universe evolves against a background temporal dimension. If time is emergent, then the universe's physical relationships produce the appearance of temporal evolution. If time is relational, then there may be no meaningful question about time without specifying which physical system is acting as the reference. If time is thermodynamic at the macroscopic level, then its arrow comes from the statistical behavior of matter and the special condition of the early universe. If time is quantum gravitational at the deepest level, then the familiar concept may need to be replaced by something that does not yet have an everyday name. The experiments have not selected one of these answers, but they have made it increasingly difficult to pretend that the Newtonian picture was the final one. And perhaps that is exactly what good experiments are supposed to do. They do not tell us what we want reality to be. They tell us where our assumptions stop working. The atomic clock tells us that gravitational potential affects elapsed time. The airplane clocks tell us that motion and gravity can produce measurable differences in elapsed time. GPS tells us that these effects are technologically important. The millimeter scale experiment tells us that gravitational time dilation is measurable across distances that are tiny on human scales. The quantum clock tells us that ticking and reading a clock are not the same physical operation. Landauer's principle tells us that erasing information has an unavoidable thermodynamic cost. The double well experiment shows that this cost can be measured. The quantum Zeno effect shows that measurement can influence evolution. The quantum switch shows that causal order can be indefinite. The Page-Wouters approach shows how internal correlations can produce an effective notion of evolution without an external clock. The Wheeler-DeWitt equation shows that a quantum description of the universe can be written without the usual time parameter. Black hole physics shows that information, gravity, and temporal evolution become deeply entangled in extreme conditions. ACEs and next-generation clocks continue to test whether our current description of spacetime survives at higher precision. And the cosmological observations remind us that even the history of the universe's expansion is not a closed book. Put all of those pieces together, and the conclusion is not time is fake. The conclusion is much more precise. We do not yet know what time fundamentally is. We know how to measure it. We know how it behaves. We know that it depends on physical conditions. We know that different observers can accumulate different amounts of it. We know that its arrow is associated with entropy and information. We know that quantum mechanics complicates causal order and measurement. We know that gravity makes time part of space-time geometry, and we know that our most ambitious attempts to describe the universe at the quantum level can no longer take an external universal time for granted. That is the frontier. The next breakthrough may come from a clock, from a quantum system, from a cosmological observation, from a gravitational experiment, or from a theory that finally explains how these pieces fit together. And when that happens, the most important discovery may not be a new way to measure time. It may be discovering that the question we have been asking for centuries was slightly wrong. Maybe we were never supposed to ask where time is. Maybe we were supposed to ask why physical systems can be related in the way that makes time appear. Maybe the universe does not move through time. Maybe the universe changes, information accumulates, correlations form, entropy increases, and we call the ordered structure of those changes time. If that is the case, then the ticking of a clock is not evidence of a universal river flowing underneath reality. It is evidence that something physical is changing in a stable and measurable way. And the fact that different clocks can disagree is not a failure of measurement. It is a property of the universe. The fact that entropy gives us a direction is not necessarily a fundamental commandment written into every microscopic equation. It may be the consequence of the universe beginning in an extraordinarily special state. The fact that we remember the past may not be because the past exists somewhere behind us. It may be because the present contains physical records of it. The fact that a quantum system can have an indefinite causal order may not mean reality is chaotic. It may mean that definite temporal order is itself a macroscopic approximation. And the fact that the universe can be described without an external time parameter may not mean nothing happens. It may mean that happening has to be defined through relationships inside the universe rather than against a clock outside it. That is where the story currently ends. Not with a time machine, not with the discovery that time has stopped, not with proof that reality is an illusion. It ends with something much more uncomfortable for physics. a question that has become extremely precise but still has no final answer. When a clock ticks, what exactly has happened? We know the atom changed state. We know a physical transition occurred. We know how many cycles define the second. We know how gravity and motion affect the rate. We know how to compare the result against another clock. But underneath all of those measurements, we still do not know whether there is a fundamental entity called time that exists independently of the systems doing the changing. Maybe there is. Maybe there isn't. And until physics can explain why the universe contains an arrow of time, why clocks behave the way relativity predicts, why quantum theory treats time differently from other physical quantities, and how a quantum description of gravity produces the temporal world we experience, the most honest answer is simply that the mystery remains. The clocks are becoming more accurate, the experiments are becoming more sensitive, the equations are becoming more complete, and somehow the nature of time is becoming less obvious. That is what makes the results so disturbing.